Bismillahirrahmanirrahim. Assalamu alaikum, dear students. Welcome to another lecture of Physics 2. This is lecture number 4th of the course. In this lecture, we will cover the remaining topics of chapter number 16. The title name of the chapter is Waves. Our main topics of today's lecture are the superposition principle. We will discuss this tool for two or more than two waves, and then the effect of the superposition principle is the interference of waves. We will discuss interference along with its types, and then the second effect of the superposition principle is the standing waves, which are also known as the stationary waves. And our final part of the lecture will be to find the position of nodes and antinodes in the standing waves. So let's start our first topic, the superposition principle. This principle gives us a resultant of two or more waves. So it is the effect of two or more waves passing simultaneously through the same region of space. For example, sound waves from many instruments fall simultaneously on our eardrum. And another example, the electron in the antennas of our radio and TV receivers are set in motion by the net effect of many electromagnetic waves from many different broadcasting centers. We consider two instantaneous displacement of wave which passing through the same string. So let y1 and y2 be the instantaneous displacement of these wave. When these wave overlaps at a single point at the same time, the resultant displacement is simply given by the algebraic equation, in which y prime is the resultant displacement is equal to the sum of the instantaneous displacement y1 and y2. The overlapping waves algebraically add to produce a resultant wave. This is the statement of superposition principle. Keep in mind, the overlapping waves do not in any way alter the travelling of each other. The interference of waves, which is the first effect of the superposition principle. The phenomena of combining waves is called interference, and the wave are said to interfere. We consider two sinusoidal waves of same wavelength and same amplitude moving in the same direction along a stretched string. So the expression for these individual waves are given as y1, which is function of position and time, is equal to ym sin kx minus omega t. The expression for the second wave y2, which is also function of position and time, is equal to ym sin kx minus omega t plus phi. Although the amplitude and the wavelength of both of these waves are the same, but the overall argument may not be the same. So for this we put a phase constant in the second expression, and in this case this phase constant is also known as the phase difference of these two waves. We can obtain their resultant by applying the superposition principle. So we will simply add these two waves algebraically. So when we put the value of each expressions in the above expression, we will obtain ym sin kx minus omega t plus ym sin kx minus omega t plus phi. As the amplitude term in both expression is the same, so we take it common and we will remaining with the sin kx minus omega t plus sin kx minus omega t plus phi in the bracket. And by trigonometric identity, Sine alpha plus sine beta, which is equal to 2 cos alpha minus beta divided by 2 sine alpha plus beta divided by 2. The kx minus omega t represent alpha and kx minus omega t plus phi represent the beta term. When we insert these terms and calculate them, our final result will be 2ym cos phi divided by 2 into sine kx minus omega t plus phi divided by 2. Is in the given expression y1 and y2 there are amplitude term and a sinusoidal term which is called the oscillating term. Similarly, we have the amplitude term in the resultant expression and the oscillating term. So the amplitude term depend upon the phase difference. So we will put different value of this phase difference and will discuss our result in next slide. In this slide we will discuss the types of interference. We have two types of interference, the constructive interference and the destructive interference. So first, for constructive interference, we took the resultant wave, which is 2ym cos phi divided by 2 sine kx minus omega t plus phi. We put condition on the phase difference. So if the phase difference is 0, then we will put 0 over here and in the amplitude term. So cos 0, if we put 0 in the amplitude term, so cos 0 will give you 1, and this one is again multiplied with the amplitude term, which will remain the same as 2ym, and this term is vanished. So our expression when phi is equal to 0 will be like 2ym sine kx minus omega t. If you compare this expression with the initial expression which were taken, so it is clearly observed that the amplitude part is 2 times. So we will call it fully constructive interference, and this is possible when the phase difference is 0. When the phase difference between two waves is pi radian, then we will insert pi over here. So this will give you pi by 2 and cos pi by 2 will give you 0. So the whole expression is multiplied with 0 and our instantaneous displacement will equal to 0. In this case, the two waves will cancel each other and we will call it a fully destructive interference. And when the phase difference is 2 pi by 3 radian, which is equal to 120 degree, then we will get y, which is function of position and time, is equal to ym sine kx minus omega t. So here in this case the resultant have the same amplitude as the amplitude were of the individual waves, and we have the same sinusoidal function. So we will call it intermediate interference. In this slide we will discuss the cases which were mathematically obtained in previous slide. So when the phase difference between two similar waves, similar means that both have the same frequency and amplitude and they are moving in the same direction. So if the phase difference is 0, then the resultant wave have a double amplitude and same oscillating term. And if the phase difference between two waves which have same frequency and same amplitude but the phase difference is pi, then the resultant wave have 0 amplitude, and this line represent that there is no amplitude of the resultant wave. And if there is a phase difference of 3 by 2 pi radian, then we will have the resultant wave of amplitude of the individual wave. Our next topic is standing waves. These waves are also known as stationary waves. To produce standing waves, two sinusoidal waves of same amplitude, wavelength travel in opposite direction along the stretched string. Their interference with each other produces standing waves. So for standing waves, two things are necessary. They must move in the opposite direction and they are traveling in a same medium. One of the outstanding features of the resultant wave is that there are some places along the string which do not move up and down. So at that point the displacement of the particle is equal to 0 and those points are called nodes. In between two adjacent nodes there are places where particles of the medium vibrate with the maximum displacement and those points are called antinodes. In this slide, the position of nodes and antinodes are graphically presented. When two waves started their motion along the same string in opposite direction, having same amplitude and same wavelength, at time t is equal to 0, the crust meet with the crust and the trough meet with the trough. So they interfere constructively and the resultant wave has a large amplitude. This green wave represents the resultant wave. After quarter time, when the crust meet with the trough, so the resultant wave equals to 0 and there is no amplitude of the resultant wave. We have a straight horizontal line. And after half time the wave again meets in such a way that the crust part of one wave meet with the crust part of the second and trough part of one wave meets with the trough part of the second. So again we have a larger amplitude of the resultant wave and so on. So the vertical line represent the maximum amplitude which is or the antinode. The maximum displacement here is the represented by the double arrow vertical line. This part is known as the antinodes and the black dotted line representing those positions where the string do not vibrate and these positions are called nodes. So the point where the string do not vibrate representing the nodes, where the double arrow vertical line represent the position of antinodes. In this slide, we will calculate the positions of node and antinodes mathematically. For this, we take two waves that are moving along a same string in opposite direction having same amplitude and wavelength given as y1 is equal to ym sin kx minus omega t and expression for the second wave is equal to ym sin kx plus omega t. Here the minus and plus sign indicate that these waves are moving in the opposite directions. And the other thing, in each expression the arguments contain the angular wave number and angular frequency, and we will compare these expression with the expression of our resultant waves. So our resultant waves can be obtained by applying the superposition principle on the given expression, which is equal to y1 plus y2 will give us the displacement of the resultant wave. So after inserting the value of y1 and y2, we will get ym into sin kx minus omega t sin kx plus omega t, and we have sine plus sine term, so we can apply a trigonometric function on this bracket. So sine alpha plus sine beta is always equal to sine alpha plus beta by 2 cos alpha minus beta by 2. Our alpha is equal to kx minus omega t, this will be our alpha, and our beta will be equal to kx plus omega t. So we will insert the value of alpha and beta in this trigonometric function and will obtain our resultant wave. So if we put the value of alpha and beta in the trigonometric function and solve the equation for the resultant wave, our resultant wave will be 2ym sin kx into cos omega t, and this resultant equation is different from y1 and y2, which were representing travelling wave. So this equation do not represent a travelling wave because the argument term is split. Sin kx and cos omega t, here the wavelength part and the frequency part are with the two different sinusoidal function. So this equation do not describe the travelling wave. The 2ym sin kx here represent the amplitude part of the standing waves, and cos omega t represent the oscillating part of the standing waves. The amplitude is 0 for values of kx, which gives sin kx is equal to 0. So the amplitude will equal to 0 if sin kx give us 0, and this is only possible that when kx takes values like n pi, integral multiple of pi. If the value of kx equal to integral multiple of pi, then sin kx is equal to 0. So if sin kx equal to 0, the whole terms is equal to 0, and we have 0 displacement of the resultant wave. And we know that the value of k, which is equal to 2 pi by lambda, we have derived this expression in our previous lecture, and so the value of node can be easily find with this expression. X is equal to n lambda divided by 2, where n takes value like 0, 1, 2, 3 and so on. So this is the position of all nodes appearing in the standing wave. So first node will appear for n is equal to 1, which is representing the origin. X is equal to 0. The next node position is when n is equal to 1, so it will half wavelength away from the origin and so on. So this formula represent all the nodes appearing in the standing waves if the wave start from the origin. In this slide we will find the position of antinode of standing waves, and antinodes are those position with where the particle of the medium vibrate with the maximum displacement. So the amplitude is 2ym for values of kx, which gives the modulus of sin kx is equal to 1. As the in amplitude part we have a sinusoidal function. If this sinusoidal function equal to 1, then the amplitude of the resultant will be 2ym, and this sin kx equal to 1 depends upon the value of kx. So this is only possible when kx takes value like pi multiple of n plus 1, where n is equal to 0, 1, 2, 3, and as we know that k is equal to 2 pi by lambda, if we insert the value of k and solve the equation for x, we will get n plus 1 divided by 2 into lambda divided by 2, and this will represent the position of all antinodes appear in a standing waves, and the value of n is equal to 0, 1, 2, 3 and so on. So if we put n is equal to 0 and multiply the half with the half lambda, so we will get the position of antinode, which is quarter distance away from the origin. So lambda by 4, so it means that the distance between node and antinode is lambda by 4, because at x is equal to 0 we have studied that that position is of node position, and after quarter wavelength we have an anti-node. So thus the distance between node and anti-node is lambda by 4. Let's sum up our today's lecture. What we have studied: we start from the superposition principle, which is a tool with which the displacement of two waves is algebraically added to find the resultant waves. And the effect of superposition principle in shape of interference has been studied along with the two types, constructive interference and destructive interference. And then we study the second effect of superposition principle, and in which two waves of same amplitude and frequency going in opposite direction produces standing waves. And in standing waves we discuss the position of nodes and antinodes. Our next lecture will be about sound and its parameters. So hopefully you will understand this lecture, and if you have any question or difficulties you can contact me at my email. Thanks and Allah Hafiz.